Today we have some exciting talks this morning, and we're going to be starting off with a new thing that the CEDAR Science Steering Committee has concocted this year, which is a joint presentation for a science highlight from a mentor and mentee team. So we're going to learn about how they kind of work together and integrate their work together. So the team here is led by Dr. Chu, and she will introduce her mentees as she goes along here. So welcome.
Good morning, everyone. Does this thing work? Okay. This is a special science highlight, which will be delivered by 3 people, mentor and mentees. My name is Xinzhao Chu, a professor from University of Colorado Boulder. I'm delighted to introduce my former student and now postdoc, Dr. Jackson Zhanzhu, and Yingfei Chen, my current PhD student, who successfully defended his dissertation on June 18th. Okay, I'm going to introduce this photo. So these 2 beautiful photos of LiDARs with Aurora and the Milky Way. On the left, it was taken by Jackson, and on the right, it was taken by Yingfei when they were leading LiDAR observational campaigns at McMurdo Station in Antarctica. The bottom photo shows me standing in front of Arrival Heights Observatory, and that's the LiDAR observatory we run in Antarctica. So today, our science highlight title is Space Atmosphere, Metal Layer, Physics, and Wave Dynamics. My team has been running McMurdo LiDAR campaign in Antarctica for, by now, about 16 years, since December 2010. We have been doing high precision laser spectroscopy in space to probe metal species, iron and sodium. So this is a famous photo taken by our first winter over LiDAR student, now Professor Zhibin Yu, showing the iron LiDAR beam, the 372, 374 nanometer iron Boltzmann LiDAR. And then in January 2018, we installed the 3-frequency sodium Doppler LiDAR to Arrival Heights, operating next to iron LiDAR. This 589 nanometer laser beam, you can see it's way more visible than the 2 UV beam from the iron LiDAR. The major science goals for us is to explore the space-atmosphere interactions in Antarctica. And here, you can see the time lapse taken by Danny Hampton. With 16 years of LiDAR discoveries from McMurdo, Antarctica, our current long-term goal is to cover 2 solar cycles. Okay, so these metal, sorry, it was went the wrong way. So you might be wondering why we want to detect metal species, iron and sodium. Where are they coming from? So let me show you this. These metal layers we detect were released by cosmic dust when burning in the upper atmosphere. The cosmic dust is a very interesting topic because they could have brought the original life to Earth, although it's debatable. It's also play a major role in the universe recycling. Just like Carl Sagan said, the cosmos is within us. We are made of star stuff. But it's not easy to detect cosmic dust. There's many different ways. For example, you can look at the zodiacal light. You can collect a meteorite from the South Pole water well. LiDAR and radar detect the metals released from the cosmic dust, the burning part. And we use these as tracers for profiling temperature, wind, and waves in this so-called space-atmosphere interaction region. This space-atmosphere interaction region is very important because it separates interplanetary space from the lower atmosphere and the biosphere, protecting life on Earth. They can protect Earth through aberrate cosmic dust, absorb harmful EUV, dissipate energetic particles, regulate atmosphere gas escape. And now, recent years, people realize they dissipate re-entry space objects. This region also connects Earth and space, and also impact society and the planetary evolution for the radio communication, GNSS, real, very real satellite drag stuff. So it's fair to say studying the space-atmosphere interactions is essential for understanding how Earth interacts with space while maintaining a stable, life-supporting atmosphere. However, it's extremely difficult to study this region because of the difficulties in observing the region. And our solutions in Antarctica at this Arrival Heights Observatory near McMurdo Station, we choose two special tracers, metal iron and sodium. They are released by cosmic dust. And also we deploy two very capable lidars, the sodium Doppler lidar and the iron Boltzmann lidar we developed after decades of technology innovation and development. With a very dedicated research team, especially many PhD students and postdocs braved through Antarctica winter. The outcomes are superb. Many discoveries resulted from these data are eye-opening, and some may be transformative to advancing the space atmosphere sciences, and some may be used to address fundamental science questions. So today, I want to show some of the results, mainly focus on metal layers and how metal layer can enable some fantastic dynamic study. This photo might be very famous. I think I've shown that over the years. The two lidars running at Arrival Heights with live volcano Mount Erebus nearby. And this is the place, the first ever discovery of TI metal layers were made. But probably very less known. Today, Qian Wu made a comment to me. They didn't know we were doing lots of science in Boulder because we have 7 years of data from there. So what is TI metal? It's a thermosphere, ionosphere, metal layers, okay? And this is the region above the main metal layers. So today I'm going to introduce you how we discovered these TI metal layers with the many colleagues around the nation and in the world. And also there's some new discovered metal transition layers. So this is a nice figure made by Yingfei. You can see he expanded our measurements from McMurdo. Data analysis from McMurdo to Boulder. Okay, so the first discovery of TI metal layers, thermosphere, ionosphere metal layers, were made from McMurdo in May 2011. So these are the main metal layers, and then we measured these metal layers goes up to 170 kilometer, this one 155 kilometer with nice gravity wave features. And using these as a tracer, we can measure temperature really apart from 30 to 70 kilometers, then from about 75 to 150 or even 170 kilometer. All depends on how much signal we can have there. So that's provide a tracer for profiling temperature. And then we have colleagues from the world measured TINA, TIK, the sodium and the potassium at both high and low altitude. At Cheryl-Poisson, Liu et al., they also use this sodium tracer, then profiled wind to about 130, 140 kilometer there. Furthermore, Rizada et al. 2015 reported the first simultaneous two species, TIK and TINA, potassium and sodium. They also had some electron measurements, so these simultaneous measurements actually challenge our current understanding. And then furthermore, Rizada et al. 2020 measured calcium ion to about 180 kilometer. Rizada et al. 2020 advocate for either probing of calcium ions as a proxy of the major ions. Fe plus, Mg plus are the major ions, but they cannot be detected from the ground due to very, very short UV light. And then in 2018, we made measurements. I published this paper, Chu et al. 2020. We have simultaneous TIFE, iron, and TINA, sodium measurements, and co-location simultaneously with aurora measurements. We found iron, TIFE, corresponding to aurora, 1-to-1 correspondence. But sodium doesn't seem to care about that. However, this volume mixing ratio shows the gravity wave features very well on the sodium. And then my first winter over student, now Professor Zhi Binyu, he's already a full professor. We came out this modeling, and we got this explanation of how these things might work there, okay? So it's, although we measured is neutral iron, but it is iron ions, Fe plus, was transported by electric field, neutral wind, then converged by orienting force V cross B, and then through direct recombination with the electrons to generate the iron. So using this model stuff, we actually also extrapolate to the lower atmosphere, lower altitude, say polar electric field, and then fountain effects around the equator. You can have these metal layers at both high and low altitude. But how about mid altitude? You know, before I made McMurdo measurements, there was decades LiDAR measurements at mid altitude, never reported TINA. Then we have Chinese colleagues reported 4 TINA events over Beijing out of 137 nights. So it's, the question is, are TI metal layers truly rare at mid altitudes? The answer is no. Because with Yingfei joining my team, we made these measurements of, we analyzed the data. The data was taken before we moved to Antarctica, and we discovered regular occurrence of TINA layer before dawn and after dusk. So these are dawn, dusk layers. And then when we use ICON, the very first use of ICON tidal winds, we were able to see these predominant TINA layers fall within the ion convergence region, so support our theory. And these bolder TINA layers are so regular. So our team was able to, mainly in phase work, able to form 12 monthly composite over 7 years. Every year you see this, every monthly composite, January through December, you see this nice downward phase progression. Then he was able to track the phase, show there's an annual variation. Summer for TINA occur early, and for the winter occur later. We used the Jens's CT-MT tidal wind, and they, surprisingly, we found the tides also have annual variations. So years ago, I made a comment, Jens did something right. Okay, so not just us, our Chinese colleagues actually developed their calcium ion LiDARs very well. So this is a paper. You can see they detected, we call it thermosphere, ionosphere, calcium ion layers, all the way to 300 kilometers. And with Shunrong's help, we try to explain this as regional vertical transport rather than coming from the equator part or coming from the polar region. Furthermore, when they moved one of their calcium ion LiDAR to the very low altitude, they detect calcium ion all the way here is 500 kilometers. But their paper was on this 1, 2, 3, 4. They think they have detected equatorial plasma bubble from the calcium ion LiDAR measurements. Okay. So then let me ask this question. Why wasn't TI metal layers discovered at mid-altitude first, despite so many years of measurements? So my answer is, first, most LiDARs didn't have a sufficient signal-to-noise ratio and high detection sensitivity. You need it to be better than 0.1 per centimeter cubic. You know, that's a very tiny signal from high altitude. And then second, it's an unknown feature, so people didn't examine it well enough. The third one is you also need a significant data processing technique in order to discover these. For example, volume mixing ratio, normalize the sodium density ratio, and use these with these significant LiDAR technology technique innovations, sophisticated LiDAR development deployment, and these dedicated LiDAR researcher. This lead to very high signal-to-noise ratio, detection sensitivity, much larger altitude range. So this enable many new sciences. I will ask Jackson to introduce the part he was excited about.
Yeah, so thank you, Dr. Chu. So Dr. Chu introduced that, one of the advantages that really allowed us to utilize a lot of this was improvements in methodology and technology over the years. And one instance of that is the development of the interleaved data processing technique, which is a technique we use to process LiDAR data, which allows us to estimate variances and fluxes with no bias. One good example of applying that was a study in 2022 that the group did looking into heat fluxes in the McMurdo LiDAR data. And one of the surprising discoveries that they found during this was positive heat flux, as you can see in those plots there on the right. Now, this positive heat flux was very surprising, and if we didn't apply these improved processing methodologies, we might not have believed it in the first place. But since we knew the methodology was solid, we then had to reflect on some long-held assumptions that people often use to estimate vertical heat flux in the atmosphere. And the group was eventually able to explain this positive heat flux that we observed by updating some approximations that were made in by applying the Bosonesque approximation to the dispersion relation. And by instead applying the fully compressible one, we were able to theoretically explain why we should see these heat fluxes, and in fact found them pretty regularly in the LiDAR data. So something I worked more on is looking at the gravity waves using these metal layers and also the Rayleigh scattering from our LiDAR systems. So you can see here two very nice observations, one I collected and one that Yingfei collected during our winter rovers at McMurdo. And in this top plot, you can really see, this is from 80 to up to 190 kilometers, you can really see nice wave structures. You can even see gravity wave features in these metal layers that we derive. So these metal layers are actually incredibly powerful for studying dynamic processes themselves directly, such as these gravity waves. And as you can see, that one phase, I think I can point, yes, this phase that reaches up to almost 190 with gravity wave periods on either side, you can see, and these lower gravity waves as well. These metal layers are incredibly powerful for allowing us to study gravity waves at altitudes that we otherwise wouldn't be able to. Not only gravity waves, but of course other wave processes like planetary waves and tides as well. In this bottom plot, you can see Dr. Chu and I had processed some data to assemble a full picture of these gravity waves from 30 kilometers all the way up to 130 kilometers, where you can see just beautiful gravity waves propagating throughout that whole region. And because these LiDARs allow us to have, the LiDARs in these metal layers enable us to have not only long duration LiDAR runs, but wide altitude runs, we can study the evolution of these dynamic processes throughout very long periods of time, including seasonally and interannually, but we can also study the vertical evolution of these dynamic processes. So in a paper we published earlier this year, we looked at taking our whole 14 plus years of LiDAR observations at McMurdo and developing baselines of gravity wave dynamic activity. When I say baselines, I mean we basically took the data and averaged it together to eliminate variability, interannual and day-to-day variability, to study the primary processes that underlie these gravity wave observations. And we were able to find consistently dissipating gravity waves, very interesting trends in the varying dissipation of those, the changes in that gravity wave dissipation with altitude. This was a very exciting paper to work on. Another paper that's currently under minor revisions right now, and hopefully we'll get that done soon, was looking at the transport processes induced by gravity waves. So a lot of you guys, especially modelers, are probably familiar with the KZZ parameter that's in a lot of models that represents the eddy diffusion of heat and constituents. This paper explored a concept, or investigated a concept that's been explored in recent years, investigating the role of gravity waves that have not broken, so not turbulence, but structured motion of gravity waves to transport constituents and heat. And what we found from this study by applying this to McMurdo baselines was actually somewhat surprising. We found that these parameters that we estimated suggested that gravity waves played a much stronger role than previously suspected in the transport of these in the middle atmosphere, or sometimes orders of, you see there around 30 kilometers, almost orders of magnitude larger than KZZ. Now that's not too surprising because KZZ is low in the middle atmosphere, but larger than KZZ in the MLT as well, and even larger than molecular diffusion for a certain range of altitudes. So while we're still not sure the exact amplitudes of these values, these are certainly an estimate. I think that these results really highlighted that these gravity waves truly do play an important role in transport and diffusion of heat and constituents throughout the atmosphere. And interestingly, this wave-induced transport actually has significant implications for the metal layers themselves, which Dr. Chu is going to elaborate on here.
Thank you, Jackson, for your wonderful presentation. Let me get back to Boulder again. Jackson was talking about McMurdo, 14 years of data. Here, I'm talking about Boulder. Using 7 years of the data we collected before we moved the sodium Doppler HIDAR to Antarctica, Yingfei and I formed this full altitude climatology from 75 kilometer all the way to 150 kilometer. So what's interesting, let's look at this. And here is the SAO, semi-annual oscillation, annual oscillation amplitude ratio. So the main layer is dominated by AO. You can see its ratio can be 0.1, very small. And then we have a huge transition from 0.1 to over 2 for this region, about 100 kilometers to 110. And then once above 120, you can see this ratio stays at about 0.5 to 0.7. So this is the sodium density. You can see this SAO, semi-annual oscillation feature. And from a mixing ratio, you can see even stronger. So why so? Look at the main layer. The column abundance is dominated by annual variation, and this is because of temperature annual variation. However, the layer centroid altitude and the layer width apparently very strong semi-annual variation there. So this is why we look for how to explain this, and this is from Dr. Chad Gardner and Dr. Zhou Shi's paper. They found the gravity wave-induced transport and the ID diffusion has this semi-annual variation, and that actually the diffusion going upward or downward at the bottom, upward at the top, determines this semi-annual. This blue is Albuquerque, New Mexico measurements. So you can see real maximum in winter, but another maximum in winter. In summer. However, this semi-annual oscillation in the gravity wave won't be able to explain TINA itself, because TINA got the maximum in summer. And for this, we want to say TINA is not a direct neutral transport, but it's this upward extension of the sodium layer width helps to enhance sodium ions production once they above a certain altitude through charge transfer, and then electric field help to transport them up. We also have the strongest nighttime electron density in summer. This helps to form this maximum of this summer. And then the two minimum, why we have this spring minimum so much smaller, that's related to the meteoric input flux, which have a global minimum in April. Yeah. So this semi-annual variation is also related to Qian et al. 2009, talking about thermospheric atmosphere number density, has a SAO which help enhance the volume mixing ratio semi-annual oscillation. So now there's some new results. I want Yingfei to introduce that.
Yes, thank you, Dr. Chu. Building on the climatology, I will introduce some newly discovered layer between the main metal layer and the thermospheric TINA layers published in Chen and Chu GRL 2026 paper. So this normalization method actually enabled this discovery. By normalizing this density by using the nightly mean of the composite at each altitude, we can suppress the strong background vertical gradient and then enhance very relatively weak structures. As shown in this February monthly composite, we can see this layer descending from about 120 kilometers to 95 kilometers. And then this altitude region actually overlaps with the very strong significant changes in the SAO to AO ratios. We believe this layer is pretty unique because it links two environments. First is the lower thermosphere that TINA layers are mainly driven by the ion transport and chemistry. The second region will be the upper mesosphere, where main layers are dominated by meteoric input and neutral chemistry. So here are the normalization method applying to monthly composite for all 12 months, confirming their regular occurrence. There are 2 points I would like to make. First is the pre-dawn TINA layers. Actually, they descend from about 150 kilometers to about 10 kilometers. This feature appears regularly in all 12 months with annual phase variations. Second, below this pre-dawn TINA layers, the sodium transition layer, they have a distinct separation, and then typically begins before local midnight near 120 kilometers, descending to about 95 kilometers. So in this case, we would like to ask whether a whole atmospheric model can reproduce such observed vertical stratification. Here are the 12-monthly composite applying the same normalization method from Beckman sodium model simulation. The model actually largely reproduced the LiDAR observed vertical stratification. The lower transition layer, I overplotted the two peak faces of the two layers onto the monthly composite from Beckman sodium. And you can see the sodium transition layer actually generally remains separated from the upper pre-dawn TINA, while the transition layer is narrower and descends more slowly, and TINA is broader and progresses downward much faster. So we can see the model also captures the vertical stratification, and those features are very clear in those 3 points here. But the model still has some improvement, as the key discrepancies will be TINA is located too high, and the transition layer also has a little bit higher altitudes. At the same time, the TINA structures are too diffuse, extending to much higher altitudes, and lacking clear downward phase progression. Combining these results leads to the following conceptual framework for the vertically stratified sodium layer system over Boulder. This schematic should be read from left to right: source, transport, and the chemistry. And finally, the observed stratification. First, the meteor ablation and sputtering provides metals primarily into the meteoric deposition region, forming the permanent main layer from around 75 kilometers to 105 kilometers. Second, upward transport from electric field and neutral wind can move sodium ions into much higher altitudes. And then with tidal winds, they can converge the sodium ions into vertically separated convergence regions. At the same time, gravity wave induce the transport and eddy diffusion, and the vertical wind, they can play important roles. Third, chemical reactions convert those concentrated sodium ion plus into neutral sodium. Then I put those detailed neutralization pathways here, but the key point is that ion transport determines where the sodium plus ion convergence forms, while the chemistry determines how efficient the ions can be neutralized and become visible to our LiDAR systems. These altitude-dependent processes form vertically connected but dynamically stratified sodium layer systems, linking the mesosphere, thermosphere, and ionosphere. Thank you.
Thank you. Thank you, Yingfei, for this wonderful introduction. So the last 2 slides, we have many more exciting data we are still analyzing. For example, last year we have TINA layer at McMurdo Station reached 250 kilometers with these very nice, this gravity wave features. And this is during a geomagnetic storm. We also, even in Boulder, we have some midnight layers. Yingfei is working on with other collaborators, and thanks to Shunrong for this TID stuff. So in conclusion, LiDAR detections of space atmosphere metal layers have led to eye-opening discoveries in space atmosphere interaction studies. and the high signal-to-noise ratio HIDAR data have enabled new inquiries into various wave dynamics, cosmic dust, vertical coupling, and this interaction of neutral atmosphere with the ionosphere, magnetosphere, and the solar wind are very important to study the Sun-Earth system. I want to say we, the CEDAR community, were pioneers in discovering and understanding Ti metal layers, Ti-Phi, TiK, TINA, calcium ion, and also the vertically stratified meteoric metal layers. But I have a message to the whole community. Now we got to catch up with Chinese colleagues on LiDAR profiling of calcium ion. They already reported to 500 kilometers and even higher. Okay? We also need to catch up with European colleagues on using LiDAR to detect human space traffic-induced metal species like lithium or aluminum stuff. Okay, so thank you for your attention. Thank you.
Okay, thank you very much. That was very exciting. We can take a few questions. If there's some in the room, we'll start with one in the room. Okay, we have Aaron back there.
Hello. It was a very nice talk.
Thank you.
I know basically nothing about sodium in the atmosphere, but it seems like what you guys described is that sodium is produced around like 90 kilometers or so, and then it's transported via like the sodium plus ions upward, and then it gets converted to neutrals, and then it descends. Is that basically right?
You got a majority right.
Okay.
There are, of course, there's gravity wave-induced transport and eddy diffusion. There are some layers going upward.
Okay.
Yeah, but then majority for the TINA, the very high ones, we tried, no way it can be neutral transport because our volume mixing ratio is bigger. You cannot transport from lower mixing ratio to higher mixing ratio. So that's why we invoke, it's the ions transport convergence, then recombination, neutralization to generate neutral sodium there.
So can you tell where the top of the eddy diffusion layer is by like where the sodium stops then?
I think potentially we can. Yingfei actually has a paper, but it's a conference paper talking about turning point. However, can we connect this turning point right around 110 to 105 kilometer? Does that mean thermopause, or even thermopause itself has no definite definition there? So we would like to collaborate with the community. How do we interpret that, and what more we can extract from the LiDAR data? Yeah, thank you.
Okay, we have time for one question, maybe from Slido. Do we have any on there? Oh, we have one in the room, so let's go with one more in the room.
Very nice presentation and very interesting result. I remember you showed the sodium can make to 350 kilometer altitude. So I
250.
wonder,
250.
250, I'm sorry, 250, averaging altitude. So what's the lifetime of the sodium when they can make to there?
Oh, that would be very long. Because by then, the only way to get rid of sodium ions would be direct recombination with the electrons, and that's a very slow reaction. So I think hours, days should be no problem. This is sodium ion, of course, also part of sporadic E. I mean, they are a minor metal ion, but the lifetime at that altitude, I believe it will be long, but we need a numerical model to confirm that.
We have our last question over here with Shenrong.
Congratulations, Xinzhao, the team, on the excellent work. So my question is on these calcium measurements. So they measured with new LiDAR. Are you able to detect with your sodium radar as well at that altitudes, or were they able to show similar results with sodium measurements? I just want to know why this is a calcium only, or this is potentially sodium radar could be detected.
Very good question, Shunrong. So the calcium ion, in principle, is easier to measure because they are there directly. Not directly, I meant they transport there. If calcium, I'll say you have sodium ions there, then you try to get a neutral sodium. It needs that recombination conversion, and usually about 1% would be converted. So it all depends on, do we have sufficient signal-to-noise ratio from the sodium IDAR? I think by now, we have the capability, and if we get even bigger telescope, more powerful laser, I think that's why we want to have calcium ion LiDAR operate with the sodium to see whether we can get them the same time. Thank you.
Okay, thank you. We're going to move on to the next talk here. Is this your phone? Okay. Did I make that work? Is that showing on the screen or not yet? There we go. Is it now? Okay, great. Okay, so I have the pleasure of announcing the winner of our inaugural CEDAR Early Career Prize Lecture, and this is Dr. Jack Moines, who received a PhD from CU Boulder in 2021 on tidal variation, and has done a postdoc at NASA CCMC, and is now a contractor for Goddard. Today, Dr. Wang will be presenting on the impact of waves and geomagnetic activity on space weather. So please welcome Dr. Wang. I'm going to reset that.
Good morning. Good morning, everyone. My name is Jack Wang from NASA CCNC. So today I talk about wave-driven circulation in the lower thermosphere. And I want to thank all my colleagues and their insight and contribution. So without them, I cannot publish all of these works. And also acknowledge the support from the NSF and NASA. So speaking of the coupling, when we think about, we often focus on the wave generated in the lower atmosphere. It can propagate upward and influence the upper atmosphere. And these waves can also deposit the momentum and drive large-scale circulations, such as the mesospheric circulation I show here. The mesospheric circulation, in the traditional view, that the mesospheric circulation is flow from the summer to the winter hemisphere, and it can control the energy budget in the mesosphere, also the temperature structures, as well as the composition. And ultimately, it can impact the thermosphere density. On the top of the mesospheric circulation, there's another summer to winter circulation, probably roughly above the 150 kilometers height. Also flow from the summer to winter hemisphere. They're driven by the pressure, mainly by pressure gradient force due to the hemisphere of symmetry in the solar heating. Between these two summer to winter circulation, the lower temperature is less understood. Actually, there's a reverse circulation sandwiched between these two layers. And now we call it the lower thermal circulation. It's flow from the winter to summer. It's very narrow, probably depends on the season. is roughly only from the 100 kilometer high to 120 kilometers high. It was first predicted by the whole atmosphere model simulation done by the Ann Smith et al. In 2011. Here I show the walk-on simulation, and the figure is the radial wind and the vertical wind in December. So in the mesosphere, that the black arrow shows there is a strong wind flow from the summer to winter hemisphere. Above, we find there is a weaker circulation reverse from the winter to summer hemisphere. However, not all models can reproduce this circulation. We later found out only the models that have the lower atmosphere components, like the walk-on or walk-on X, that can reproduce this winter to summer circulation in the lower thermosphere. So the figure I show here is the TIGCN circulation, and in January, and the TIGCN, the lower boundary is around 97 kilometers high. And that here, we only find there's a two-cell circulation, poleward moving in January. So over the last 5 years, we try to study this lower thermal circulation. And to answer, to study this, the circulation, we have 3 key questions that I will try to answer today. Can we observe the circulation directly? What is the driving mechanism for this circulation? And why does it matter for the whole atmosphere? So to start, can we observe the circulation? Yes, but the first clue came from the indirect observation. The figure I show here is the stable CO2 observation, and this study is done by Chen et al. In 2017. On the left, that is the stable CO2 observation in July. On the right is in January. Below around about 85 kilometers, that is the CO2 is well mixed. But above then, the gas start from the well mixed state, move toward the diffusely separated. If we look closely to the vertical gradient of the CO2, you will find some interesting feature that we can talk more about. So there's a maximum the vertical gradient of the CO2 that at summer is down at mesosphere, but at winter hemisphere, the maximum of the vertical gradient of CO2 is higher up in the lower thermosphere. This must suggest that there has a convergence of the upwelling below and downwelling above along this convergence zone. So back to the circulation pattern we have. So the red line, on the right side, I draw a diagram here. If we connect to the mesospheric circulation and the well-known mid to upper thermal circulation, we must need a circulation in between to balance this vertical wind, this lower thermal circulation. But this is just an indirect evidence. So can we directly observe the lower thermal circulation? So let's try to see if we can use the tidy to reveal this reverse circulation. So we use the tidy on board the time and meridional wind observation between the 85 kilometers high to 105 kilometers high. They provide day and night observations, but tidy's time satellite is near sun synchronized, so we need around 60 days to connect all 24 hours local time. That is important because we more interested in the mean circulation. So we need to have the 24 hours local time data to avoid the tidal aliasing into this mean wind expansion. And here is the result. On the top, I show the tidy 60-day and diurnally mean meridional wind at 105 kilometers high. On the bottom shows the same meridional wind, but at 90 kilometers high. So clearly, in the 2008 and 2009. So clearly, we find at around 90 kilometers high, the winds from the summer to winter, and on the top, the wind circulation reverse to the winter to summer circulation, and the magnitude can reach about 15 meters per second. So yes, we can observe this circulation directly from tidy. Such features can also reproduce by SD-100X. And here I show the residual meridional wind as a function of the latitude and height. So we can also find this reverse circulation sandwiched between these two well-known summer to winter circulation. The magnitude is a little bit weaker, probably only around 5 to 10 meters per second. So to answer our first question, can we observe this circulation? Yes. Tidy reveals a robust lower thermal circulation from the winter to summer, and WACON-S reproduce the observed circulation pattern. But we also find some discrepancy between the observations and the models. So because the WACON-S can reproduce these features, so we can use the WACON-S model result, model output to study the mechanism to answer what is the driving mechanism of this lower thermal circulation. So to understanding this, the driving mechanism, we probably need to analyze the zone mean, zone momentum budget. So don't panic, let's try to break it down a little bit. So first, we can roughly neglect of the local tendency, because on the seasonal time scale, the local time tendency is small. And we can also perform some scale analysis. We find in the lower thermosphere, the vertical advection in the zonal mean zonal momentum budget is only play a minor role. So now the equation becomes much friendlier, but still contains important physics. So once we have the wave forcing, the circulation must be response to balance the wave forcing we deposit in the lower thermosphere. So we can use this equation to study what is the wave forcing turn is more important to driving the circulation pattern. So we can move the square bracket from the left-hand side to right-hand side. So we can have the directly meridional wind output from the model. We can also use the wave forcing expansion from the WACON-S output, then put into our equation to estimate this circulation magnitude. On the top is the meridional wind expansion from the resolved waves. On the bottom shows same, but from the parameterized gravity wave. We find in the SD WACON-S, this lower thermal circulation is mainly driven by the model resolved waves forcing. So what's the driving mechanism? These circulations are mainly driven by the resolved wave forcing, and that includes tides and the planetary and the gravity waves. So what is the impact? Let me show you just one example. So here I show the atomic oxygen ready to change to the annual average in June. On the left is the result from the ANSYS. On the right shows the result from the SD WACON-S. So interestingly, we find that around 90 to 100 kilometer high, we find that this atomic oxygen has a phase reversal on the seasonal timescales. And SD Warheads can also reproduce this result. So connect to what we have known that the CO2 vertical gradient. Let's try also calculate the vertical gradient of the atomic oxygen in models. So if we calculate this vertical gradient of the O, we will find there's matched with our circulation patterns very well. The large atomic oxygen vertical gradient in the winter hemisphere is higher up in the lower thermosphere, and the larger there's also a secondary maximum of the vertical gradient of the atomic oxygen in the summer mesosphere. This means that there's lower thermal circulation and this vertical wind associated with the low thermal circulation can have the impact in the atomic oxygen in all seasonal behavior. So why is it important? Because atomic oxygen at around 90 to 110 kilometers high is very close to their source and sink region. So this lower thermal circulation is play a role like a dynamical driver that define how much atomic oxygen is available that can diffuse or transport to the thermosphere. That can have the direct impact to the mass density in the thermosphere, and also define the absolute value of the mass density, and also define the preconditioning of the mass density. Xinzhao just told you about the turbopause in their talk. So one of the definitions of the turbopause that by Linson in 1981 is he defined that turbopause is the attitude where the molecular diffusions and additive diffusions are equal. But for the tracer, like CO2, water vapor, or atomic oxygen in the lower thermosphere, this definition might not be accurate because the vertical advection associated with this lower thermosphere circulation can dominate over additive diffusion. So the turbopause is not just one single height. It's probably span tens of the kilometers in the lower thermosphere. So why does it matter for the whole thermosphere? Why we need to study this circulation? Because the advection associated with the lower thermal circulation can efficiently transport all between its source and sink region within the vertical columns in the lower thermosphere. And vertical advection appears to play a dominant role in the seasonal atomic oxygen variability. So the turbopause is not just a single height, it's more likely a turbo layer, a broad transition region where molecular diffusion overtake eddy diffusions and the vertical advection. So to summarize, the TIDE reveals a robust low thermal circulation, and SD Warheads reproduce the observed circulation pattern. And we also find, through the SD Warheads, we find the low thermal circulation is driven by the model resolved waves, including the tides and the gravity waves. It can have a great impact. Vertical advection associated with the lower thermal circulation can efficiently transport atomic oxygen between its source and sink region within the vertical column in the lower thermosphere. So if you find this study interesting or relevant to your work, there's also some advanced published just in these 2 years. One is by Dr. Dai Koxin. He used the high-resolution Warhang S to further study the driving mechanism of this circulation. And the other paper that done by us, and that we find this circulation can also modulate the middle and upper thermosphere above the 150 kilometer height. And shares similar concept. The circulation can also significantly change during the SSW event. Many colleagues in the CEDAR community also done tremendous work in this study related to this circulation. And I will encourage you to read their papers. First by Dr. Fasul Laskar and Dr. Jens Overhey, also the Dr. Jiarong Zhang and Dr. Osorini. So this is my last slide. Last night I tried to find a photo from my computer. First, I attended a CEDAR workshop first time in 2014, and that at Seattle. I just graduated from a bachelor degree. My first time to CEDAR, and my first visit to United States. And I still remember Professor Jens Hofer standing in front of my poster, say, "You are doing wrong." His intuition is right. We went back to Taiwan. We find there's a bug in our simulation. And we spent maybe 2 or 3 months to debug our code, and later that year, we published my first paper. There's many similar conversations throughout my career. So I just want to say thank you, CEDAR community, for opening the door to my career and to the NSF support throughout the way. Also to my advisor, Rowan Zhang, Scott Pello, and Jia Yue, their mentorship and shaped my path from the beginning. Thank you.
Okay, we'd like to open it up for questions in the room.
Jack, great talk, thank you. Regarding the mechanism, the largest uncertainty in that equation you show, which is, by the way, the downward control principle, the largest uncertainty is the gravity wave drag, obviously. Right. So is it fair to say that when the circulation is not well represented is because the gravity wave drag parameterization is wrong?
Exactly, yeah. Yeah.
I think this is related to the last question. The WACMX does a great job. Excellent talk, by the way. WACMX does a great job, but it's not getting all the gravity waves. It's not getting the small-scale gravity waves. And so I don't know what that's going to end up doing to the circulation, at least in the models. And so I just caution, you know, when you say your results come from the WACM resolved waves, it's missing some, clearly.
I just want to make one comment, because we use a 1 degree resolution, so we can only resolve the waves down to the wave number around 30. And the parameterization, the current WACMX we use, that only include the phase speed between minus and positive and minus 45 meters per second. So it's quite narrow. We have a more high speed of the gravity wave. Yeah, so Dai Koshin, that the paper that I just mentioned, their study that I think they move another step forward, because their high resolution WACMX, they can resolve more gravity waves realistically. Yeah.
So great lecture, Jack. I really enjoyed that. So I'm certain you looked into relative importance of different wave types, right?
Yeah.
I mean, can you comment a little bit about the relative importance of planetary waves versus tidal impacts on the circulation?
Yeah, for the circulation, that our result is contrary to the Jalon, because they find that planetary also play an important role. But from our result, we found a planetary wave contribution is pretty small. And for the tides, we find that D3 and SW2 is important, play a major role in driving this circulation. I hope I answered. Thank
it will just turn on.
Can
if
you hear
turn-
me? That was a wonderful talk. Thank you so much. Can you speak a little bit to hemispheric asymmetries or seasonal asymmetries in the circulation? How does it vary south to north winter and in the northern and some southern hemispheres?
You mean this one, right? Or yeah. So we not exactly know why there's a asymmetry there. But from Dye's paper, they find there is some higher order of the tidal waves. Then can play some rules, but we don't have observation to find out. Also, this asymmetry can play a role because we know SAO, AO, yeah, we still don't know what is the driving mechanism of the AO in the mass density. This symmetry probably can play some rules in the AO. That's we need definitely more observation to further study, and probably also some other sensitivities that can probably answer this question. Yeah.
Thanks very much for the talk. This is Roger Varney from UCLA. I'm struck by how narrow in altitude this circulation is. So what, from a physics perspective, is so special about 105 kilometers that causes this circulation to form specifically there and not lower at 100 or higher at 130?
Good question. So most of the waves, they need to dissipate because the molecular diffusion is so strong above maybe around 110 kilometers high or 115 kilometers. So all the gravity waves that propagate from downward, probably outward from the troposphere or maybe stratosphere, they need to dissipate. So the wave forcing must be deposited in this very narrow region. And down in the mesosphere, we form the mesosphere circulation, but it can also form a critical layer that can filter some gravity wave out. We have some higher speed gravity wave that can probably upward, but it's the opposite, so phase speed. So that's why they can, once these wave forcing, this wave depositing their momentum, they must be reversed to the mesospheric circulation, right?
Jack, thank you for your nice talk. I was actually intrigued by Roger's question to you, because whatever that very narrow our atmosphere circulation overlap with the transition layers altitude almost exactly where Yingfei has been studied. So there, for the transition layer, apparently it's tidal winds has some phase there very strong. So I want to ask you, do you think this tidal wind could have something to do with this gravity wave dissipation? But apparently there's waves propagate upward, as shown in our CEDAR measurements.
Right.
I want to hear your thought.
I think so. I think so. So, but to answer this question, that I mean, I feel they're all coupled together. So we do not specifically to study if the tidal wind can play a role in the gravity wave filter or something. So we, in our studies, we more focus on how the large-scale circulation respond to the old wave forcing that we input. So I'm probably not the right person to answer this question. Probably the Professor Overhigh is, yeah, right.
So one follow-up to the question, the answer you just gave. If I understood you right, you were saying the gravity wave were breaking or above 100 kilometers, 104, 105 kilometers. But I would think the gravity waves would be breaking close to the mesopause where there's a steep temperature gradient. So either 80 82 kilometers, 85 kilometers, or 98 kilometers, but not up at 105 kilometers. So it's a little puzzling to me if you're arguing that the gravity waves are predominantly braking and depositing the momentum up at 105. So what I'm saying is that based on the temperature gradients, I would think the braking of waves would be more likely to occur closer to where the mesopause is. So it's either like into the 80-kilometer region or the upper 90s, but not up at 105 kilometers or so. So if your answer was, if I understood your answer correctly to the previous question, that a lot of the gravity waves are braking, depositing the momentum up at 105 kilometers, that's a little puzzling to me.
Yeah, I will take the liberty to say a few words about this. I think most of the gravity waves, they break in the mesopause, but some high phase speed gravity waves, they break above that. And also tides dissipate at this altitude that forms this lower thermosphere residual circulation. Yeah, high phase speed.
Okay. Thank you all, and thank you, Dr. Wang. Okay, next we have a CEDAR science highlight by Dr. Jean Liu on the impact of atmospheric waves on geomagnetic and geomagnetic disturbances on space weather. So welcome. And this is the laser pointer. Okay, I'm going to reset this.
Okay. Good morning, everyone. So it's my pleasure to share our work on collective impacts of atmospheric waves and geomagnetic disturbances on space weather. So this work has been funded by NSF Answers. So we really appreciate the great support from NSF, which enabled great collaborative collaboration among a few institutions. I would like to acknowledge my co-Is of this grant, including Jens Alberheider, Scott England, Shunrong Zhang, Chris Hill, Lindsay Goodwin. Also, I would like to thank the former and current graduate students working at Clemson, including Haonan Wu, Ben Martinez, Deparli, Aragwar Shri, and Prakash Powder. So the overall science goal of our project is to explore relative contributions of geomagnetic activity, lower atmosphere waves, and solar irradiance to the variability of space weather during both quiet and storm times. So as you can see from this diagram, which kind of highlights the overall methodology of our project, it has three important forcings to the IT system. So on the left is magnetospheric forcing, and the middle is low atmosphere wave forcing, and also solar UV forcing. So our team members spent tons of efforts, and they did a great job to really improve the model drivers to be as realistic as possible. So we want to first capture observations and to interpret the data from the great science satellite missions from ground-based data. And once the model we think is doing a great job, then we feel more confident to use the model for mechanism studies and for better predictability, for example. So, and as you can see, this is a little complex diagram, and it also involves a lot of data model cross-comparison, validation, involving a lot of data sets, and this is truly a collaborative work. And we had 3 team meetings. First one at Clemson University, and the last one we had last year was at Embry-Riddle. We have great team members here, and especially in July 2024, we also hosted a virtual student workshop. We gave tutorials to students from 10 countries, from over 40 institutions. So that's the teamwork. And then let me back to the science. I want to start from magnetospheric forcing. So one work that we did is we improved these aurora maps and the electric field maps by doing the assimilation. So the framework we adopted is so-called lattice-Kringin multi-scale data assimilation. So one thing about this framework is it could locate the base functions. In this case, it could be very localized base functions with multi-resolutions at locations that we really want. For example, if you have more observations at a certain location, you can give that finer grades to capture more variabilities of your aurora and electric field. So then you can see, compared with these empirical models, after data assimilation, you start to see these mesoscale aurora features. And if you compare with this observation, the background, which is like empirical models, has bigger arrows. And if you go to the higher and higher resolution of data assimilation, the arrows really goes down. And the multi-scale is also very good capability, because later on we can say divide these magnetospheric forcings into different scales and try to figure out different scales, what are their contributions to the IT. And later on, so we further improved this data assimilation and adopted from just using for scalar, which is aurora, to vector. So then we are able to use the same framework to not only assimilate aurora, but at the same time assimilate electric fields. So you can see this is a Pfizer observations for 2015 St. Patrick's Day storm. We have this around 6 UT. There was a big electrical northward electric fields causing significant Joule heating deposited into the IT region. From empirical, it's missing. And from data assimilation, once we incorporate these local Pfizer observations of ion drifts, you can say locally, this feature is resolved. Okay, so now we use this aurora and electric fields, which are the two most important magnetospheric force, represent magnetospheric force into IT. We use, one is driven by empirical maps, TIE simulations, driven by empirical maps. The other one is TIE simulation driven by the data assimilation, data assimilated aurora and electric fields. And then you can see for the data assimilation, we have bigger waves, bigger TIDs that's with larger magnitudes, and also they could propagate more towards the equator. So first of all, a simulation run is way more realistic. Second of all, we also see more significant spatial and temporal variabilities enhanced by a factor of 2 to 3. And if you imagine this is wave, and the energy of the wave is proportional to square of your amplitudes, so could increase by an order of magnitudes. And we also compare this with the Pfizer observations of electron density, which is the first row, and the ion temperature, which is the second row. So remember last slide, I mentioned that there's an increase of northward electric fields happened around 6. And from observations, you can see the ion temperature reached over like 4,000 K-ish. And from the empirical run, driven by empirical maps, nothing really shows up there. But if we use the more realistic forcing, you can see the model simulations. This is the model simulation by TIE GCM. Captured this increase of ion temperature, and at the same time, because of the particle precipitation, TIE GCM also captured the enhancement of electron density in the E region and the lower F region. So we do think this is very important to incorporate and for the model to do a better job. Okay, so then my student Prakash Powder used this assimilated capability, and he ran TIE GCM, and we simulated the TADs during a relatively quiet period enabled by the GOLD graduate campaign. We collaborated with Scott England on this work. So KP is kind of like a 2 to 3-ish for these events. And then you can see the empirical aurora quite smooth, and assimilation captures more scales of forcing and localized stuff. And this is the TADs in vertical winds that's generated by aurora forcing in the polar region. And then if we compare the GOLD observations with TIE GSM simulations, you can see the model can nicely capture observations, for example, the dependence of wave amplitudes on the geomagnetic index. We see this nice positive correlation indicating aurora origin for the TADs from GOLD, and TIE is doing the same thing. And in terms of wave propagation, mainly meridionally, propagation direction is also consistent with GOLD observations. So now let's move on to lower atmosphere wave forcing, and I'm going to start with gravity waves, because gravity wave is also one of the very important origin to cause the disturbances in the IT. So this is a joint or GNSS observation that happened during May 9th, 2024. So there was a tornado outbreak in the lower atmosphere. So all observed very nice wave patterns, and the GNSS also showed nicely these concentric rain patterns. So Sri did very nice work in correlating the wave perturbations in the MLT region observed by all with the GNSS observations. So she did a statistical study of gravity wave TID coupling. So basically, she checked whether the wave from the MLT, you can find the similar wave patterns, similar orientations, then she characterized that as a gravity wave TID coupling. So she did that for the whole year, and then she kind of, tried to quantify to what extent, what is the percentage during quiet geomagnetic condition and during active geomagnetic condition, what are those coupling events? And not surprisingly, I would say quiet time, we have more events that can be showing up, and that's more than the active time. And Sri also did a nice work using GNSS, showing the majority of the waves propagating northward. Likely, it's probably because maybe your convective center is south of the region that we are looking at, and about like 14% of the wave propagating southwestward, which might be related to Perkins instability that people are also discussing. Okay, so I think on Monday's plenary session, there was a question asking, say, whether this type of, say, tornado or thunderstorm events can be simulated in a realistic way, and the answer is yes. So what we did is we took the MAGIC simulation. So MAGIC simulation can kind of, it's also in a very realistic way, is say they took the latent heat from the surface, for example, and the MAGIC has very high resolution and can nicely simulate gravity wave perturbations all the way up. And what we did is we nudged the gravity wave fields into TIE nasty grid model. So TIE nasty grid was developed by my former graduate student Haonan Wu with the advice of Dr. Wenbing Wang at NCAR. And this, the second row, then you can see this simulation, we have like, I think we have 3 grids. The global one is 1.25 degrees, and this is the finest resolution one is about 0.3 degrees. And if you compare the model simulation about this event showing these concentric rain patterns with the model, with the GNSS, I would say model is doing a very good job in simulating the evolution, the magnitudes, and the propagation. All the things are really well simulated. And a nice thing, once you think your model is good, is you can use the model to infer things that are not observed. For example, the impacts of your wave on other variables, like vertical winds, for example, and in this case, the impacts on vertical winds is actually quite significant, 60 meters per second. Usually from storm, the magnitude would be also like maybe 50 or 100 meters per second for really big geomagnetic storms. And we also find perturbations in neutral density 10% and ion drifts about 100 meters per second. Okay, so this is same simulation, but we looked a little bit away from the center of the wave and to the far fields, and very luckily, ICON and Cosmic 2 have, we were able to find the overlaps with these two data sets at far fields, and we also compared with the model simulations, which is the black line here, with ICON, yellow line, and with Cosmic 2, red line. So these are the ion densities showing here. And you can see very nice matching of ICON and Cosmic 2 observations along the track. Okay, so now let's talk a little bit about the lower atmosphere forcing from tides. So we know that for sun-synchronous, quasi-synchronous, sun-synchronous satellites, usually you need to accumulate, for example, 30 days for time, 60 days for time, then 30 days for ICON to kind of collect enough local time to get the tidal results. So more than often, the results are a little bit kind of smoothed. So I think that the real day-to-day variability is very difficult and challenging, and still, this is a very hot topic for the community to solve right now. But my colleague, Jens Alberheid, he found a very creative way using mighty ICON to tackle, not very smooth, but it's more like very real day-to-day tidal variability in the MLT region, as shown by this black line. So this is the standard deviation, which is a proxy of day-to-day variability of these 3 tides for the zonal wind from mighty. So this is 103 kilometers. And I want to echo Xinzao's comment. So Jens did a right thing again. And you can see, because you can see that if we compare the day-to-day variability of D3 tides in the MLT region with the Cosmic 2 day-to-day variability, which is around like 500 kilometers, and then you can see they match very well. So those are 2 independent data sets. And also the day-to-day variabilities of these 2 data sets are kind of derived using different way, because Cosmic 2, we have every hour, we have the data, we derive day-to-day variability, but ICON, Jens find out a more like a statistical way, and to get, for details, well, you can refer to Jens' paper. So this kind of matching indicates 2 things. So first, the methodology of using ICON to derive day-to-day variability is robust. It shows good results. Second, more about science is that for DE3, the E-region dynamo is a very important mechanism to transmit the variability in the MLT all the way to F region. So there's 2 things we can learn from these results. So then what I did is I incorporated all the tidal components derived from ICON with day-to-day variability of tides. So basically, it's not smooth results. It really has day-to-day variability inside of the data at the low boundary. Then we nudged that into TIE GCM, which represents more realistic forcing from tidal waves from below. And then from the comparison, you can see TIE GCM, this is showing the 2 tidal components, D3 and SW2. So this is showing 2 to 35 standard deviations at every single point. So this is the day-to-day variability of D3 and SW2 in electron density. And you can see how nicely they match the observations from Cosmic 2 data. So we're not saying like a single point that they match, but you can see the seasonal variations, the latitudinal distributions, and even some intra-seasonal variability is captured by TIE GCM. So I think we're very happy about these results, and it does provide a tool to realistically estimate relative contribution from lower atmosphere and solar magnetosphere forcing to IT changes. So there are really a lot of great things going on, and we're very excited about what we're doing, but I do not have time to go through all of the work. But if you're interested, you can actually check our websites and talk to me. And for CEDAR, 2 more talks. I want to point out, one is from my former graduate student, and he just graduated and joined the USU as a postdoc. So Ben Martinez is going to talk about machine learning and predictability for space weather at right after this at the GC2 workshop. And Friday, Xiaoyu Sun is going to talk about the geomagnetic storm impacts on orbits. Okay, so to conclude my talk, ANSYS quantified and demonstrated how the simultaneous use of data-constrained lower atmosphere and magnetospheric forcings leads to a substantially better quantitative simulation of the average in ionosphere across small to large spatial and temporal scales. And you can see from the comparisons is the realistic forcings resulted in a larger and more realistic dynamic range of ionospheric variability with potential to better space weather predictability. And we got exciting news for CEDAR is NASA is funding the dynamic team, which is really exciting. And I think this newly developed model and the simulating tools will be very useful in the future for interpreting the forthcoming dynamic data. And as a member of the CEDAR community, I'm very excited and look forward to working on it. Thank you.
Thank you. Can we open it up for questions?
Very nice talk. Can you go to slide number 11 or 12? I can't remember exactly. No, this one. Okay. So TEC is an integrated quantity, and it doesn't tell you where this wave is highly dominated, at what altitude. But I can say you can do it altitude by altitude on your model using TiGCM. Did you, I don't know, try at what altitude the wave is dominating in modulating the density?
Yes, I think in our paper we showed the NE perturbations at different altitudes.
Okay. And can you say the altitude? What altitude the gravity wave is dominating?
In terms of altitudes, I think the most impacts still occurred when NE is big. The background NE is big. Then when you wave perturb, you get the bigger amplitudes for the perturbation as well. So I would say it's probably from 200 to 300 kilometers. That's the range.
Okay, thank you.
Okay.